So, hi, good morning, everyone. Let's go ahead and get started. It's 10:10. Thank you, everyone, for joining us this morning. It's my honor to introduce our Warren Lecture speaker today, Professor Andreas Malikopoulos, who's a professor in the School of Civil and Environmental Engineering at Cornell University. He has spent time before joining Cornell at the University of Delaware at Oak Ridge National Lab and as a researcher at General Motors. He has a long list of accomplishments and awards. Notably, he's a member of the Board of Governors of the IEEE Intelligent Transportation Systems Society. I think I'll use less time to give you more time. Andreas, the floor is yours.
Great.
Thank you for joining us.
Thank you so much. Thank you for the introduction. It's great to be back to campus. I've been here 10 years ago when Sunny invited me to give a seminar, and it was again October, at that time. So what I plan to do today is to discuss how we can combine learning and control in cyber-physical systems and focus more on the areas of transportation. Our world is changing, and one particular sector that undergoes significant transformation is transportation. We're about to depart from conventional vehicles with typical internal combustion engines and move on entirely to electric vehicles. And this transformation will provide several challenges and also opportunities. We have the challenge to upgrade our existing transportation network with efficient charging stations to charge all these electric vehicles. We have the opportunity to create technologies that can sort of handle the increasing demand of electricity from all these vehicles. We have the opportunity to integrate these vehicles with commercial and residential buildings so that we can have eventually off-grid buildings. And then on top of that, we do have the introduction of connected and automated vehicles with shared information. And using this shared information, we can improve the transportation efficiency and also reduce energy. So if you look at all these applications, there is a common theme. We have a cyber component, which is data or information that we use to control the physical entity. So we have a typical cyber-physical system. So now you might wonder why we need to focus so much on transportation. Well, in 2017, the US alone consumed on average 19.6 million barrels of petroleum. And transportation accounted for 71% of that usage. If you think about it, this is enough fuel to fill up the entire building over 2 times per day just to propel the vehicles. So you can see the impact of transportation in oil displacement. Now, with the introduction of connected automated vehicles, we have significant opportunities to use connectivity and automation and improve the efficiency of the vehicles, and so account for this sort of impact that of transportation. So what I plan to do today is I'll go through some projects that I have worked over the past years in learning and control, applying to propulsion systems and also in connected automated vehicles. And then, through this path, I will try to highlight the challenges of the learning and the model-based control. And then at the end, I'll try to convince you that and make the case that if we combine learning and control, we are better off in this particular case. So before I get started, let me acknowledge the contributions of my students in the IDS lab. In my lab, we develop control algorithms and theories that we can use to make cyber-physical systems able to realize their optimal operation while they're interacting with the environment. And the focus is mainly, the majority of the focus actually is on transportation and emerging mobility systems and smart cities. To validate our work, we have built up a scale smart city. This is a 20 by 20 feet or 6 by 6 meters, if you are familiar with the SI units. We have about 50 cars. Everything is in scale 1 to 24. And we have cars and drones, and we can use this testbed to go one step further from simulation. We can, test some of the algorithms in different scenarios. You can prove concepts, different transportation concepts. For example, we have done, coordination of a drone with a car in the first and last mile delivery. We can use the drones to act as a coordinators in specific scenarios and handle the information from the cars and then use this information to do better controls. So this is a nice testbed that you can use experiments and train students without having safety concerns. We have also integrated a driver emulator into the cars. So essentially, we can drive the cars in the city, and we can have an environment between mixed traffic, between human-driven robotic cars and fully connected automated cars. The cars have a little camera ahead, so the driver can see through the camera and the monitor what's going on in the traffic conditions. So as you can see, there is a little camera ahead as the student drives the car, and then we can see the environment through the monitor. We also can use these cars and this testbed to prove some cooperative control for ground and aerial vehicles, like these kind of cases when we have a platoon of vehicles and a drone that oversee the vehicles, collect information from the surroundings, and then report back to the vehicles. We have also built a digital twin of the city. So this is a digital replica, the twin city. And eventually we use this with our collaborators that they can have access remotely and do some experiments. And then when their algorithms become mature, then they can come and do some physical testing in our scale city. We also built an app that can replicate shared mobility like Uber and Lyft. So you can download the app, and then you can call one of the cars to come to the origin, and then you can identify an artificial destination, and then we can use this app to validate some of the eco-routing approaches that we develop in the lab. So eventually you have multiple users, assigning different origin destinations, and then you have a little traffic going on, and then you can validate and quantify some of the results that we do. The city was featured in the IEEE Control Systems magazine last December, so we were pretty happy about this. And we also have a driver simulation testbed with 6 driver emulators that we can use with commercial software to do some very basic simulation stuff. And typically, this is where we started. We started with a simulation, and then move on to our scale city. So that was a little bit of introduction and acknowledgement for the work of my students. Coming back to the technical talk, over the years, I have had the chance to work on different problems in transportation. I started with my dissertation when I eventually work on learning control and how we can make the engine in a vehicle learns its optimal operation with respect to the driver's driving style. And then I moved on and worked on hybrid electric vehicles and plug-in hybrid electric vehicles and how we can develop power management controls to improve the efficiency. And over the last 14, 15 years or so, I've been working on connected automated vehicles and how we can use shared information to optimize efficiency and also improve safety. So what I plan to do today is I'll go through my journey. And throughout this journey, I will highlighting challenges in learning and control. And then at the end, I will try to make the case about how we can combine learning and control in those kinds of applications. So my journey started in 2003 when I joined University of Michigan. I arrived in Detroit in the winter, because in Michigan, you can start either in January or in September for graduate school. There was about 11 inches of snow in Detroit, and coming from Greece, it was a big shock for me. So the first thing that I had to do is to get around the weather, and the second thing was to find an interesting topic for my dissertation. So I was going through different articles to find out an interesting problem, and I came along this question that was very common at that time. Why we cannot achieve the miles per gallon that are posted on the window sticker of our cars? So I thought that this was an interesting question to dig into and understand a little bit more. So let's see what's going on. When we buy a car, it comes with a window sticker from EPA, and they give you fuel economy estimates for highway driving, for city driving. And although we can almost always achieve the highway miles per gallon estimates, we can barely achieve those corresponding to the city driving. So let's see why is this the case. Now, to understand how engine operation works, and actually William is the right person to ask, we need to look at the engine operating domain with respect to engine torque and engine speed. These colorful contours that you see here is the so-called brake-specific fuel consumption map, the BSFC map. And this gives you fuel consumption per unit power. So the lower this value, the better it is. Now, as we drive the vehicle, this is the speed profile of the vehicle. As we drive the vehicle and we accelerate, if you look at the engine operating domain and the BSFC map, we see a point jumping around. This is the engine operating point, and corresponding, follows it evolves as we drive the vehicle. Now, depending on where the point stands in this map, we have the corresponding fuel consumption. Now, how OEMs calibrate the engine? Well, they typically take the engine operating domain and discretize it to a finite, typically small number of steady state operating points. And when I say steady state operating point, it means that we operate the engine at constant torque and constant speed. And then they went to these steady state operating points and they find out the optimal values of the controllable variables, ejection timing, spark timing, you name all the available values that we have in our disposal. And then we take all these maps, we have a big map, and then we put this in the electronic control unit of the engine. And as we drive the car and we accelerate, and the engine operating point goes around, we interpolate the values of the controllable variables corresponding to the steady state operating points, and this is how we control engine eventually. Now, at that time, some colleagues of mine in Autolab at U of M, they did some experimental work, and they found out the following. If we operate the engine at a steady state operating point at constant torque and constant speed, we have pretty much constant fuel consumption. And this is why we can achieve the fuel economy estimates for highway driving, because the engines have been optimized for steady state operation. Now, if we approach this operating point for a sequence of engine operating points, however, we get fuel consumption varies for a small transient period. And moreover, if we approach this operating point from a different direction, fuel consumption is associated with different values. So when we drive the car in a city, essentially we operate the engine in these transient operating points. And this is why we cannot really get the fuel consumption estimates posted on the window sticker, because these estimates are based on steady state operating points. Now, to optimize the engine for all these transient cases a priori is infeasible, right? Just because every driver drives different and they have an infinite dimensional space of different engine operating points transition. So you can't really do that a priori. So what I did in my dissertation, essentially, I took a different approach, and instead of focusing on steady state operating points, I focused on the engine operating points transition. And I modeled the engine operating, the evolution of the engine operating point as a control Markov chain. And then I will start learning as the driver drives the vehicle, the transition probability matrix. So eventually, we came up with a controller that can learn the transition probability matrix dim characteristic of the driver's driving style, and eventually derive an optimal engine calibration corresponding to the driver's driving style. So with this approach, as the driver drives the vehicle, the engine captures the driver's driving style through the transition probability matrix and eventually derives the optimal calibration. With this approach, we were able to see an improvement about 8% in most of the case studies, which was significant just to get some of those results by just calibrating the engine in a different way. Now, this is the good aspect of the story, but as I promised, I'm going to highlight the challenges in this case. Now, once you do this exercise with reinforcement learning techniques, let me put it this way, you start from a feasible engine controllable set that you want to explore what's the optimal values, but eventually you might try some controllable values of the controllable variables that may stall the engine, right? So, and even if you say that, okay, I'm going to be careful how to define my feasible domain so that I will avoid any abnormal operation of the engine, if you take this feasible domain to a different state, let's say from Michigan to Nevada, this feasible state set will change. So the message here is that you can't really rely entirely on reinforcement learning because you just cannot really ensure robust operation of the engine all the time. So you need to have some sort of baseline operation and then leave a little bit of space into your controller to learn the optimal values, but then you minimize essentially the space that you can all the bandwidth that you have to optimize your engine. So there are some trade-offs, and this is the first challenge that I want to highlight. And this is under the category of reinforcement learning techniques and whether you can apply reinforcement learning directly onto your system. And then I moved to GM in R&D, and I worked on a similar problem. So at that time, the focus was on developing a new engine combustion technology. And then we required to have multiple small injections, precise injections. And we couldn't afford to use piezoelectric fuel injector. These are characteristic curves of a solenoid injector. You have 4 injectors, and you have 4 different injection curves on 2 different cylinder pressures. So you can see that if you have these 4 fuel injectors into your engine, once you command the pulse width, you get 4 different fuels. So you create some instability inside your engine. So the project was how you can learn these injector curves so that you can precisely inject the fuel that you want to inject. And you can think that this is a very pretty straightforward problem, like system identification. I have this curve, I just need to identify this curve in real time. Well, the problem is that when you inject the fuel, you don't have a sensor inside the cylinder to measure what's the amount of fuel that you have injected. So essentially, you try to do control without having feedback. You can only have a air fuel ratio into your engine, and this is again, you don't have individual air fuel ratio in the cylinder. So eventually, what I end up having is I had a bunch of data for fuel injectors, offline data, data that I can have pulse width and fuel, but experimental data, not data from the engine. And then I use supervised learning, and I created a super type of controller. But again, I could not rely on this data entirely on supervised learning. And the reason was that you have the injector behaves different inside the engine and different if you have an experimental setup. So eventually, I had to adapt the supervised learning with the neural networks with some sort of adaptive control that can account for this type of instabilities. And then starting from a baseline calibration, that was this line. These are the true, I hope you can see those. There's very light color. But anyhow, these are true fuel injector curves at a small, mass. I was able within a few cycles, meaning a few milliseconds, to get some samples and then learn the true fuel injector curves while the engine was driving, while the engine was operating. So that's another, type of, and we were able to achieve at least 4% improvement with this approach by being able to identify precisely the fuel injector curves. So the message here is that if you use supervised learning now, again, you cannot really rely entirely on the supervised data that you have, on the data that you derive offline. You need to sort of kick in some sort of adaptive scheme into your system so that you can account and get into the equation the real-time data. Then I moved on to Oak Ridge National Lab after GM, and I had the chance to work on hybrid electric vehicles and plug-in hybrid electric vehicles and how you can essentially derive power management control algorithms to optimize the efficiency. So before I get to that, let's discuss what is a hybrid electric vehicle. Well, with a hybrid electric vehicle, in addition to the engine, you have motor, generator, and battery that you can power the vehicle either separately or in combination. So as the driver asks for power, this power can be delivered through engine only, or through the motor only, or through a combination. And then if you use the motor, you deplete the battery. So at some point, you have to command the engine to send power to the generator and charge the battery. So there is a multiple decision-making process and a lot of degree of freedoms that you have available to optimize the whole powertrain system. So in this map, you can see, this is the BSFC map that I discussed before. You can see the point, this is the torque demand for the driver, and the blue is the engine, the motor torque, and the magenta is the engine torque. So you can see how the torque demanded by the driver is being delivered through the motor and the engine. And as you use the motor, you deplete the battery. This is the state of charge of the battery as you accelerate. So there is a multiple, a little bit of complex decision-making inside the powertrain that you need to do in order to optimize the efficiency of the power. So the way we approach this is first we identify the feasible state action pair of each of the subsystems, the engine, motor, generator. And then you can use multiple criteria, different criteria to formulate your problem. Typically, we use the total cost criterion, which is derive the optimal control strategy to minimize the cost or maximize the efficiency for a given time period, which is the driving cycle. In this case, I use the average cost criterion, which means that I want to optimize my powertrain for the long term, like as the driver drives the car for days, weeks, and months. Now, to solve this problem in real time, it's kind of infeasible, just because you need to solve this problem for any different driver as the driver drives the vehicle, and you don't have the computational power on board to do that kind of thing. So what I did in this problem, I reformulated the problem, and I created a multi-objective problem where the objective here to maximize the efficiency of every single component, engine, the efficiency of the engine, the generator, motor, and the battery. And I solved this problem offline. So I had the map of the engine, the BSFC map. I had the maps of the motor and the generator. So I solved this problem, and I create the Pareto solution of these different cases for every single realization of the engine torque, demanding torque. And then I took this map and I put it in the model, and I was running the model by interpolating the values corresponding to the Pareto solution. And I show, at least theoretically, that if you operate under this Pareto optimal solution, you essentially minimize the average cost criterion. The average cost criterion, not the total cost criterion. And we did some also simulation studies. We ran the model with a Pareto control policy in real time once, and we got some fuel economy results. And then we use reinforcement learning to mimic the dynamic programming solution. So we essentially took the same model and we ran it over the same driving cycle again and again and again and again until it converts to the optimal strategy that was corresponding to the dynamic programming. And we saw that we get pretty much the same solution with some sort of, some numerical, tolerance. Now, we also went and did some experiments with our demo vehicle. We had an Audi A3 plug-in hybrid electric vehicle that was part of the ARPA project that was completed a couple of years ago. And we compared the solution with a Pareto controller to the Audi's controller. So as you can see, that was an experiment that did our collaborators, Bosch, did. So you see, this is the BSFC map. This column corresponds to the thermal efficiency. So you need to have it as high as possible. You can see that in case of the Audi's controller, the engine operating points are spread out, right? Although with the Pareto control policy, we have squeezed all of them into the higher efficiency regime. And this is why we got almost 12% improvement in the powertrain compared to the solution that we get from the Audi's controller. So that's kind of how we could validate what we were expecting from the theory. So we went ahead and we implement this in a different problem. When I was at Oak Ridge, we had a project to make a building off-grid, dispatching the electricity demand from the residents to different resources, renewable resources available, like wind. You have photovoltaic panels. You have also a car integrating, an electric car integrating with a building. And the idea was how you can dispatch all the electricity demand of the building into these resources and make the building to not require any electricity from the grid. It's typical, if you think about it, this is very similar to the hybrid electric vehicle, right? Instead of asking for torque, you're asking for electricity, and you dispatch this into the. And we applied the same approach there, and we show the different type of results. And then at that time, when I was at Oak Ridge, I started working on connected automated vehicles. I saw the opportunity when I was working on the hybrid electric vehicle that if you have additional information from the traffic, you might be in the position to do better controls. And eventually, I was thinking that in addition to safety, you can use this share information from all the vehicles and sort of avoid situations like this when you have congestion. So the question was, if I use this information, can I coordinate the vehicles in intersections, in roundabouts, in merging roadways, and avoid the stop-and-go driving? So And if you think about it, actually, this was not a new idea. I mean, in 1939, actually, in the New York's World's Fair Futurama, they had a big model about the world, and one big portion of that was about transportation, and they envisioned how transportation would look like in the future. So they envision a very efficient highway system where the vehicles will cruise in a high speed in a safety matter. In 1956, GM featured the car into the future, 20 years into the future. So they envision in 1956 a car that will be completely autonomous. They have this gentleman represent what we call today GM on Star, if you have a GM car. Essentially, the GM on Star gives some directions to the driver, and then the driver, get to the dedicated lane, and then from that point on, the car is completely autonomous and goes to, the family goes to Chicago, and they show that the kind of luxury benefits if you have a fully autonomous vehicle. Now, that was in 1956, and it's 2023, and we still kind of have a vision about how autonomous cars would look like, which speaks to the complexity of these problems, right? We're getting there, but we still have a way to go. So eventually, in this movie, they showcase all the type of benefits that you can have if somebody else is driving the car for you. So long story short, over the last few years, we have worked on control algorithms, model-based control, that we can use to coordinate vehicles in intersections, in multiple intersections, in roundabouts, and so forth and so on. So let me take the time to go through the problem and show you what's the challenge in this case when we do model-based control. I'm going to refer to an intersection, but the analysis here can apply to any other traffic scenario, like roundabout or merging roadway, or you name it. So let's assume that we have 4 vehicles approaching the intersection. If they keep cruising, eventually they will have some collision at the center of the intersection. This area at the center of the intersection that we have a potential lateral collision is called merging zone. And then we define a control zone around the intersection and outside the merging zone, inside of which the vehicles can communicate with each other and can change information. So the problem is the following. If we assume that all the vehicles are connected and automated, once the vehicle enters the control zone, to derive its optimal acceleration, deceleration, so that it can cross the intersection and also exit the control zone on the other side without collision and with a minimum fuel consumption possible. So if you think about it, let's take a closer look. We have the vehicle. At the time that the vehicle enters the control zone, it has to derive the timing that will be entering and exiting the merging zone, and then also the time that will be exit the control zone. Once it fixes the times, then it will have to derive an optimal acceleration, deceleration all the way through so that it can cross the control zone without stop-and-go driving, without collision. Now, if you think about it, this is a 2-level problem. In the upper level, we want to find out the optimal timings that will crossing the merging zone so that we can maximize the throughput of the intersection. In the low level, we want to maximize the fuel consumption, minimize fuel consumption, maximize fuel economy, minimize fuel consumption for these times, right? So in our approach, first, we model each vehicle as a double integrator, where P is the position of the vehicle starting from the entry of the control zone, V is the speed, U is the control input, acceleration, deceleration, and S is the intermediate distance from the preceding vehicle. So this is the distance from the vehicle I from the preceding vehicle K. Now, somebody might argue here and say, hey, you model the car as a double integrator model. This is far away from the dynamics of a true vehicle. And that's true. That's a fair argument. And that's the disadvantage of model-based control. You have to use a very simple model just because you need to derive your control strategy in real time. Now, what we typically do now here is that you use the double integrator model to derive your optimal acceleration, deceleration, an optimal trajectory, essentially. And then you use a lower-level PI or PID controller to track this trajectory. That's how we design cruise controllers. So you bypass this by this trick. But again, this is one of the highlights that I also promised about model-based control. There's a discrepancy between the model that you use and the real system. So you don't expect the optimal solution to be the true optimal solution eventually. Now, once the next step is to define the upper bounds of the control and state. So essentially, every vehicle has the maximum acceleration and braking capability. We need to incorporate this in our framework, and also we impose some speed limits inside the control zone. And then we address the safety constraints. So for each vehicle I needs to maintain at least a safe distance S. I'm sorry, delta from the preceding vehicle. And by the way, this safety distance is also a function of the speed of the vehicles, because the higher the speed, the higher the distance that you need to maintain from the preceding vehicle. And then we have also the lateral collision safety constraints, which essentially guarantees that we don't have lateral collision inside the merging zone between the vehicles. Once we set up that, we are ready to formulate a low-level optimization problem, which is minimizing the control input of the delta norm of the control input from the time Ti0 that the vehicle enters the control zone until the time TIF that the vehicle exits the control zone. Now, somebody might say, hey, you said that you're going to minimize fuel consumption. How is this related to fuel consumption? Since you minimize the L2 norm of the control input, this doesn't have energy units. Well, if you remember from the BSFC discussion before, when you minimize the control input, you minimize acceleration. If you minimize acceleration, you minimize transient engine operation. And if you minimize transient engine operation, you mimic steady state operation, which is how you get the fuel consumption benefits. So eventually, by asking to minimize the L2 norm, we minimize all the transient engine operation, you mimic the steady state operation, and this is how you get all the benefits. Now, to solve this problem, you formulate the Hamiltonian analysis and the Hamiltonian function, and then if none of the state, control, or safety constraints become active, then you have a nice closed form analytical solution where the optimal control input is then a affine function. The optimal speed is a quadratic polynomial, and the optimal position is a cubic polynomial of time. Now, this is the case when none of the state, control, or safety constraints become active. You have a very nice closed form solution that you can implement in real time. Now, the problem is if any of the state, control, of safety becomes active. In this case, things are getting complicated. So this is the case when none of the constraints become active, we have a very nice closed form analytical solution. But if any of the state, control, or safety constraints become active, then what we need to do is to piece the constraint and unconstrained arcs together to satisfy Euler-Lagrange equations along with the conditions, the boundary conditions and interior conditions of the corners here, the junction points, T1 and T2, which leads to a set of high nonlinear algebraic equations that we need to solve simultaneously. And this is the case that implies that we need to have a numerical solution, which means that we cannot really implement this in real time on board the vehicle, right? So this is how the whole process, the whole approach falls apart. If you cannot really implement this in real time, then there is no point to go any further. And if you get any solution, then let's say that you get a solution, then this solution might hit another constraint down the road. So you need to repeat this process. Just to give you a flavor of the complexity, let's assume that the rear end constraints becomes active. If this becomes active, then it imposes discontinuities in the influence function of the Hamiltonian analysis. And then essentially you end up with a set of algebraic equations, these algebraic equations that you need to solve simultaneously. So you can see the kind of the level of complexity that you add to the problem. So the way to bypass all of that is the following. The whole idea is that can I derive a solution that eventually don't activate any of the state, control, or safety constraints? That was the idea. If that's the case, then I can stick to my unconstrained solution, which is a closed form solution. That's the cubic polynomial, right? If none of my state constraints or safety constraints become active, I can solve the problem in real time. So we start from this, and if we observe this equation, this is the optimal polynomial, the optimal position of the vehicle for the unconstrained case. You can see that this is a real value function. It is increasing, and it's differentiable, which means that this is one-to-one function, which means that this is invertible. You can find the inverse. As a matter of fact, you can use Cardano's method and you can compute the inverse of this function, meaning time with respect to the position. And we call this time trajectory. So time trajectory means that you have the time of the vehicle with respect to the position, with respect to the control zone. So what's the time that the vehicle will be at this position inside the control zone? Now, if we use this time trajectory, and let's say that we have all the time trajectories for all the vehicles inside the control zone, let's say that these time trajectories are these black lines. These are three vehicles that crossing the intersection. So that's how time trajectories look like in this graph. These are two other time trajectories for vehicles going along the way with our vehicle. So if that's the case, if I have all the time trajectories for all other vehicles inside the control zone, once my vehicle gets at the entry of the control zone, I just need to derive a time trajectory, avoiding intersecting any of the existing trajectories. If I don't intersect any of the existing trajectories, it implies that I don't activate any of my state control or safety constraints. Now, once I derive this, eventually I need to minimize the time at the exit of the control zone. Because remember, in the upper level problem, we want to minimize the time that the vehicles will be exiting. So eventually, I can find the shape of my injector time trajectory curve that gives me the minimum exit time, but at the same time doesn't intersect any of the. Now, if you think about it, this is the solution of the entire problem, because now once I derive this, I can inverse back, and this is the new polynomial function of my low level control. So I solve the problem by minimizing the time without intersecting any of the state control or safety constraints. Once I do that, I inverse back, and I have the analytical solutions of the unconstrained problem. So that's the idea to address this. Just to give you the math context, eventually we start with this equation, and we evaluate this equation at the end of the control zone. We evaluate it at the position at the time. We invert first this equation with the Cardano's method, and then you have a function of the position, and you evaluate this at the exit of the control zone. Eventually, you end up having a function of phi, of the coefficients phi, that will give you the shape of the time trajectory. And then this is your objective function. Of course, you need to incorporate all the quality constraints that accommodate the interior and boundary conditions. For example, you have initial position at the entry of the control zone, the position at the exit of the control zone, the speed at the entry of the merging zone, all the boundary conditions that you can have available. And then you also consider all the inequality constraints in your problem, like the speed, the maximum speed, the maximum acceleration. You put all this together, and eventually you end up having a nice problem formulation where you're trying to minimize the exit, the time trajectory at the exit of the control zone, subject to these constraints, right? Now, the question is, can I solve this problem in real time? That's the big motivation at the beginning. Well, it turns out that the objective function is a convex function. And the equality and equality constraints, the set of equality and equality constraints, is affine functions. So you can apply the Slatter's weaker condition here, and you can show that essentially the problem doesn't have any duality gap, which means that you're dealing with a convex optimization problem that you can solve in real time. We apply this approach to different scenarios in intersections, merging roadways, in corridors. Let me show some results. The first experiment was in our scale city in an intersection. So we have different vehicles getting into the intersection, and then they derive the optimal time trajectories, and they can cross the intersection without stop-and-go driving. And then we also include a corridor in our scale city that included an intersection and roundabout and a merging roadway. These are about 15 vehicles, if I remember correctly. You can see how the vehicles going through the roundabout, the intersection, and the merging roadway, and they all coordinate. Now, in this problem, we have three different control zones. So we didn't include one single control zone, three different control zones, independent with each other. And then they can go through all the corridors without stop-and-go driving. We also did some experiments in M-City with our demo car. That was part of the ARPA project that was completed a couple of years ago, led by UD. Our collaborators was Bosch, the industrial stakeholder, University of Michigan, Bosch, and Oak Ridge National Lab. And the goal of this project was to improve the efficiency of the Audi by at least 20%. William was leading another ARPA project in the same team. So we did experiments in M-City. In M-City, they have the augmented reality. So essentially, you have the car running in the field, and then they create a bunch of virtual cars that broadcasting with a physical entity. So you can have your car in doing experiments and interacting with virtual cars. So as you can see here, you will see the car, the Audi in the M-City, and then this is the virtual simulation when you have the Audi and all the virtual cars. In the top of the video, it's the baseline scenario without connectivity and automation. And in the bottom, you will see the video with connected automated vehicles and the Audi running without control algorithms. So as you can see, the Audi comes through the ramp and interacting with the virtual vehicles. There is no vehicle, of course, but that's the virtual vehicles, the black vehicles. And then there is a gap that can switch in and get into the merging zone without stop and go driving. Although in this case, there is a black vehicle, a virtual vehicle ahead that blocks the Audi proceed. So they're trying to find an appropriate gap to squeeze in what we encounter today, right? And then, of course, the Audi can get in. And so with this, setting, we were able to do experiments and validate the control algorithms without safety constraints. We also did some experiments in Bosch Farmington Hill facilities. Eventually, we put the Audi in the chassis dyno and went through the virtual driving inside the M-City. On the left, you can see the baseline scenario without connectivity and automation, and on the right is when the Audi and all the vehicles runs with our control algorithms. As you can see, the Audi, in this particular case, we have a lot of stop and go driving because the Audi have to come to a full stop at some point, right? Although on the left, we have eliminated all the stop and go driving just because the vehicles can coordinate and cross the merging zones without stop and go driving. So eventually, by eliminating this, you have sort of translated the city driving to a freeway driving, right? And this is where you get the benefits, ranging from 13% all the way to 34%. Now, you might think that this might be high values, but if you compare the miles per gallon of your car between highway and city driving, those are the differences essentially. So by eliminating stop and go driving, you get the benefits by having a freeway type of driving. So we've seen so far three different problems. We've seen the model-based control that we use for the connected automated vehicles problem, and there is a discrepancy between the model and the actual system as we discussed. And I had to do the trick with a PI controller. I just derived the optimal acceleration using the double integrator, and then I use the PID controller. So the bottom line is that model-based control cannot facilitate solutions with performance guarantees. That's the bottom line. For the supervised learning, if you recall, we can't really rely entirely on supervised learning and offline data, just because these have some implications in the robust operation. If you remember in the fuel injector example, I had to use some adaptive schemes to account for that. On the other hand, in the reinforcement learning, you can't really apply reinforcement learning directly onto the system because this has implications on robust operation. If you remember, in this case, I can't really start entirely from scratch learning the optimal calibration of the engine because I might select a controllable variable that can stall the engine or create some abnormality. So let's see how we can combine learning and control in these problems and get the benefits out of it. Let's assume that we have a cyber-physical system, an actual cyber-physical system. Let's see, you might be a connected automated vehicle. And then we have some disturbance on this system, typical disturbance. And then we have some noisy outputs in this system, right? You want to make some outputs. And then we have a model, an appropriate model that we can use in parallel with our actual system. So this is a typical, let's say the double integrator that I used before. Now, the idea here is that if I can institute an information state that includes information from the state of the actual CPS and the model that I have available, and then use this information state to derive the optimal control strategy offline using the model. Now, if I pause here, I don't do anything different from what we do today. Today, we have an actual system. We have a simple model of this system. and we use the simple model of the system to derive an optimal control strategy, and then apply this optimal control strategy to the real system. I do the same thing, but now instead of using the state of my system, my model, I use the information state. But the information state has information about the state of my actual CPS, which is when I go offline, this is unknown because the actual system does not operate offline, right? Which means that what? When I derive my optimal control strategy now offline using the model, this control strategy will be parameterized with respect to all realizations of the actual CPS. So I derive an optimal control strategy, which is parameterized with respect to all the values, potential values of the state of the actual CPS. Now I take this control strategy and I apply it to my system. And as I deriving data, I start learning the information state online. And once my information state becomes known, then the optimal control strategy that I derived offline is optimal for the actual CPS. So that's the idea. Let me give you another layer of details. We have recent papers here that they provide all the details if you want to dig into this. So essentially, let's assume that we have a system. This is the actual CPS. Xt hat is the variable of my actual CPS, ut is the control input, and wt is the disturbance. All these are random variables defined in appropriate probability space. And then we have some also noisy output, right? Xt again is xt hat is the state, and zt hat is the noise, the error of my instrument that I measure the output. Now, the problem now, this is the actual CPS. The problem is to derive the optimal control strategy that minimize the total cost, the total expected cost. And as I said, we can't really solve this problem, just because we don't have the true dynamics of the system. We need to use a simple model to do that. Now, we use the simple model, and then we establish an information state, which is nothing different but the conditional probability distribution of the state of my model and the actual state of my system, given all the data of my model. Now, if I can show that this information state does not depend on the control strategy, then eventually I separate the control from the learning, and then I can use this information strategy, this information state, to derive my optimal control strategy in real time, offline, using the model, right? Just because I have shown that this is separated. And then once I derive the optimal control strategy offline, I can apply it to my model and my actual CPS. And then remember that this control strategy is parameterized with respect to all the values of the actual CPS. I can use this to learn the information state offline. So this is recent work in progress, and we are trying to implement this in some transportation mobility systems, but we eventually believe that this approach can help us address applications when you have data in dynamic nature that they're added to the system gradually and not altogether in advance. So you can, instead of relying entirely on supervised type of approaches, you can use this combination of learning and control, derive your optimal control strategy offline by knowing what's going on under the hood, and then left some of this task online to use learning and complete the work. So with this, I would like to thank you for your attention. I'd be happy to take any questions.
Thank you. We have time for a couple of questions if there's any questions from the audience. There's also questions perhaps on Zoom that we should be checking. Anyone from the audience? Otherwise, I have plenty. Go ahead.
I have any questions too. Oh, sorry. Let me use this.
Yeah.
Okay. A lot of your work on energy, because that's my area. But so with regards to the transient engine operation or transient vehicle operation and reduction in fuel economy, how much is that due to acceleration versus jerk? Right? Are we talking about reducing jerk as opposed, because clearly the vehicles need to accelerate, right? Can you comment on that a little bit?
So jerk is in our formulation, we consider jerk for comfort of the passengers, and we focus on. You're right. I mean, you can't really eliminate acceleration because you have to accelerate. But what we're trying to do is just to avoid unnecessary acceleration or smoothing out the acceleration to the point that you can mimic steady state operation. But the objective is on the L2 norm of the control input, which is acceleration. We don't consider jerk. We have considered jerk as another complementary function to account for the comfort, because eventually we end up seeing that the solution that we get might provide discomfort to the passengers.
Motion sickness.
Yes.
Yeah.
So you need to account with
Yeah, of course. And then I have one more quick question. So, going back to your early work, nobody was talking about physics-informed neural nets or physics-informed learning back in the days that you were doing that work, right? Have you considered going back and including PIN as sort of a, I don't know, I would say redo, but as a new, because physics constraints are something that you're clearly missing, right?
Yeah.
So is it something you consider going back to?
Yes, we do that with the latest approach. We still have a lot of work in progress to be made, because we're trying to understand a little bit more the theoretical aspects and the computational aspects. For example, it sounds very appealing, learning this conditional probability, but actually to learn this conditional probability is quite challenging. This is what we're getting. So yes, the answer is yes. We're revisiting some of these old days with different approaches, but we haven't seen a clear path yet, just because there are other challenges coming along.
Yeah, I mean, your work on the intersection, vehicle control to pass through the intersections, that's very interesting. What happens if some of the vehicles are not, they're manually driven, they don't, you don't know what they will do essentially, but some of the other vehicles are being controlled.
Yeah,
Is there a way to handle those?
Yeah, that's a great question. So yes, what I show today, it implies that all the vehicles are connected and automated. But if we have human-driven vehicles, a mixed traffic, then things are getting complicated, because essentially you don't control the human-driven vehicles. So what we have done is we have used Bayesian approaches to interferes to sort of, instead of having a trajectory, we have a trajectory, a tube of the trajectory, an interval, inside of which we have some confidence that none of the vehicles will intervene. So, and what we do, we observe the trajectories of the other vehicles, the human-driven vehicles, and as we observe and collect data, and we're trying to quantify the uncertainty and reduce this tube eventually. So with Bayesian interference approaches, we're trying to, we translate this to a robust optimization problem essentially, and we're trying to collect data from the human-driven vehicles and then get some confidence as we log. Of course, if you do this in an intersection, you have very, the whole process is very fast. Just cross the intersection. So there are some also challenges in that perspective. Another approach that we have looked at is how you can make the connected automated vehicles, behave in a way to create platoons of vehicles. So a CAV creating a platoon of human-driven vehicles, and then use the CAVs to control the platoons. But then again, you acting as the jerk, and you decelerate, and then you create platoons, and then you control. But again,
so CAV is kind of the lead of the platoon.
Exactly. Every platoon has a CAV lead, and then you control the CAVs. But again, if you control the CAV and command the CAV to accelerate, you don't have guarantees that the HTVs will accelerate as well. Of course, you can assume the car following model, but this is not a human-driven model, right? It's a car following model. In simulation can work, but in reality it might not work. So again, if you have a completely signal-free intersection, we don't sure that the driver will be willing to cross the intersection without coming to a full stop. So we consider intersection with stop signs and how you can create a gap that the human-driven vehicle will always have a clear path to cross. So the bottom line is that this is a quite challenging problem, a much more challenging problem. We have benchmarked the solution, but as you add human-driven vehicles, then the solution, the benefits of the solution fades away.
Okay, thank you.
I'm mostly bothered by your conception of a city. I didn't see any pedestrians or bicycles, pedestrians mostly. It's as though you've decided that there are cars as little bugs in the city, and that's all there is in a city.
That's a great point.
Doesn't this, I mean, it's beautiful, don't get me wrong, incredibly clever, but it seems like you're optimizing the wrong problem.
Absolutely, I agree with you. So the idea and the vision behind these solutions is that you have, very high efficient transport intersections and roundabouts and so forth. But then you can have nice bridges for humans to cross around, right? Like they have in many European countries or in Las Vegas. If you go to Las Vegas, they have these bridges that the pedestrians. So you maximize the efficiency of the thing. Of course, you don't have to have this solution in every single intersection possible. You can just focus on those high, intersections with high travel demand, and then create these nice bridges that pedestrians can cross safely around, or with and then you can have other intersections that can just be regular intersections without or for pedestrians only, or for those. So it's bottom line is it's really hard to get to the efficiency by allowing pedestrians to get mixed up with it's just there's a safety concern. So the idea is to have a paradigm shift. If we agree that this is a viable solution by allowing having bridges, pedestrian bridges, small bridges that pedestrians can use, and then have the vehicles, then we can guarantee safety and also exercise the pedestrians a little bit, just to to elevate some. So, but this is a different problem. This is an urban. We need input from policy scientists or other expertise just to make this consensus.
One more question.
Yeah, sorry, just I didn't get that part. We have different control zones. Who is responsible for controlling those zones? Because I think this is a kind of distributed method, independent, or if they are responsible for sharing information, who is controlling those zones?
Yeah, great question. So every control zone has a coordinator. The coordinator is, let's say, a roadside unit that can store all the time trajectories for the vehicles. And then each vehicle can, infrastructure, right? And each vehicle can, access the roadside unit and access all the existing time trajectories. So imagine that the coordinator is sort of the common thing of the intersection, doesn't do any controls, but collects information from everybody, and everybody has access to this information. So it's sort of centralized all the information available, and then the vehicles can make informed decisions. For example, once my vehicle enters the control zone, it accesses the coordinator, gets all the existing time trajectories, and then solves the problem, and then moves along. Right. So again, this is not centralized control, it's central information. Each vehicle has its own controls, right? So each vehicle accesses this information, but it does their own control. It's not a central central controller, but you're correct. If you have this information get hacked, then all the vehicles are. That's the cybersecurity issue, which we don't address. But if this is secure, then that's how it works. All the vehicles get access to this existing information inside the control zone, and then they can do their own controls. So every vehicle can have its own controller, essentially. It doesn't have to be centralized. Now, the question is, what if you have two intersections next to each other and the control zones overlap? That's the problem. Then in that case, we consider a single control zone for both intersections, or you can sort of have to do a little bit more work to combine, because you might have a road with multiple intersections close to each other. And then you can't really have the whole corridor. It becomes, intractable, So this becomes more and more, for example, when we did the corridor in the scale city, we have this issue because the intersections were close to each other and they had to overlap. So we have to, find very precise the boundaries between the control zones to address this.
Okay, well, thank you very much. Thanks to the audience for really active participation and engagement here. And thanks again to Andreas for joining us today. Thank you.